Hello, and we're back making use of things like these with things like these. That's right, it's the Part 2 Decoding Rotary Encoders. Last episode we talked about creating signals from a rotary encoder with our DIY breakout board that we made. This was great for getting the ideas of how these operate down. However, there are some changes that I made that now that we're moving on to processing the signals, it's important that we cover. First, I flipped the diagram upside down, and consequently A and B are now going to be in the opposite positions. Next, I changed the resistors here, our pull-up resistors, to 100K, and the 15Ks here were convenient for driving the LEDs that we had as a visual. However, if we were trying to use an output here, the signal would not be strong enough because the voltage drop would just be going straight through our LEDs, and our outputs here would be useless. So I removed those, and also changed the capacitors here from 150 nanofarads to 10 nanofarads, and that's just so that we have the same debounce effect that we had with our 15 and our 150 with our 100 and our 10 nanofarads. Finally, I altered the push button circuit here as well, just because it's a terrible design. If you look at this, this wouldn't even work, and I've learned a lot since the last video. So now we just have the 10K and the 150 nanofarads, so the same values here, but instead of connecting the ground to the components, the 5 volts is connected via this switch here, and then we take our output right here from where these two components are connected in. That way we'll get a positive going pulse every time we push that button. And that's it. There are 2 bits of information that we can get from rotary encoders, and that is going to be whether it's been turned 1 indentation, and we're going to be calling that the clock signal. And then it's going to be the other bit of information is whether it's been turned left or right, and we'll be calling that the up-down. And so we call them these, I call them these names because when you're interfacing them with ICs, it's usually the name of the pins that we're going to be connecting them to. So this is the common way of visualizing the signals that we're going to be receiving from pins A and B when we turn our knob. And as we covered in the last video, there's a repeated pattern that we get for each indentation that we turn through. So we can dissect these patterns into 4 different sections, which can be represented with 1s and 0s. So you can look at it as A and B are 1 and 1 right here because they're both going to be in a high pulled up position, and then it's going to continue on as a 1 0, and then a 0 0, and then 0 1, and then it ends back on a 1 1. And this may be helpful for you, or it may not. This is just something that I use to help decode in my own way. And of course this pattern is going to be reversed when it's in the turned in the clockwise versus counterclockwise direction. So instead of it being 1 0 here, it's going to be 0 1. And so you can see here that the knob was rotated clockwise because B was dropped low first, and as we see here in our previous diagrams, when it's rotated in this direction, B is, we're actually going to be looking at the new one here, B is going to have contact made on it first, because as we're turning it clockwise, this wiper will first contact B, driving it low, as we can see here in this timing diagram, so that B will go low each time that this is turned clockwise, B will go low first, and as it's turned counterclockwise, A will go low first. So here is the updated board here. You can see I have 100Ks here where I used to have 15s, and I have the 10 nanofarads here as our debounce circuit. And then right here we also have the 100K, and it's flipped upside down, but this is the 150 nano for our switch, our push button switch. The way we're going to put it on the board though is exactly the same. We're hooking one side up to the push button, to our positive rail, and then we also have down here our negative and our positive, and then our two A and B that we're getting out. And so we just go ahead and push that in. And then to visualize this, as we don't have the LEDs anymore, I'm just going to toss in some LED driver circuits with an Npn transistor. The ones that I like to use are these BC547s. And here's that circuit right here. So when I turn it on, they're both pulled high by the internal 100K resistors here. And as I turn it clockwise, as we expected, B goes low first, then A, and then B comes high, and then A comes high. And even though it's not essential to the operation of the rotary encoder, especially when I'm breadboarding, I really like having this visual confirmation of what's going on. There are some ICs that don't require any additional circuitry to our breakout board. And the one I know of for certain is the digital potentiometer here, the X9C either 10K, or I'm sorry, 1K, 10K, 100K, or 50K. I have the 100K right here, and it's a little bit different than some of the other digipots you might be familiar with, and that's that you can connect the rotary encoder directly to it. And what you do is just connect terminal B to our increment pin right here, and then A to the up-down, and the wiper of the potentiometer will be moved up. Here's this very poorly drawn potentiometer here. The right hand one being this pin here, and the left hand and the wiper being up there. These lines over the top here is to show that it's an active low, which means that for the increment, we're going to be using our clock pulses here. They're going to be negative edge triggered, so that each time the increment pin goes low, it takes a look at its up-down pin right here and decides whether or not to move the potentiometer up or down one increment. And in the case of the XC104, it's just 1K that it gets moved. So it has 100 possible positions through this through the 100K that are in here. And so when B is pulled low first, right here, the up-down pin will reference pin A, and since in this case where it's turned clockwise, it will reference pin A at this point when it goes low, and since it's high and up is active high, it will be moved up or counterclockwise, just as when this is turned counterclockwise. And same for when it's, let's say you were to turn it counterclockwise, pin A will go low first. However, the digital potentiometer does nothing until the negative going edge here of B, and then it will reference pin A, and since the up-down pin here is down is an active low, so that it takes a look at A, it's low, and so it will be moved in a counterclockwise rotation inside of the digital pot and move it down 1K. So in my limited experience, negative edge triggered clocks are not that common, such as with the increment pin here on the X9C chip, to where it took action once the pin here on B went low. This is the instant when it took a look at what was happening at A and decided whether or not to go up or down. It's considered a negative edge triggered clock, and most are positive edge, to where it would take action during this phase right here of our B. And if we were to plug the B into the clock here of, let's say, our 4029 4-bit presettable counter here to our rotary encoder, the results would be erratic and unpredictable, and in some applications it wouldn't work at all. However, we can invert or flip our B signal here so that we are getting positive pulses here instead of negative pulses. We'd have a fairly functional system, identical in operation as the digital potentiometer, where B is going to be our clock source, and then our up-down source is going to be A, and it would be referencing the A pin every time that the B would have a rising edge, and determined whether or not whether or not the incremental up-down counter would count up or down is dependent on whether it was turned clockwise or counterclockwise. So let's take a look at that on the breadboard. So now to invert our B signal, or to get it to do the opposite of what it's doing right now, so instead of being on normally, and then as you turn through an increment it goes off and then back on again, I'm just going to use a very simple circuit. If you're not familiar with it, it's just a transistor inverter. And so we're going to have our B signal here coming in, and I'm going to put it through a 1 mega ohm into an Npn transistor again, and that's going to be pulled high through a 100K. And so every time that our B signal is high, which is normally, this will be our 100K here, or the point in which we're going to take our output, is going to be pulled, is going to be sank low. And so right here at our output we'll get a low signal while this is high, and then once B goes low, this will no longer be conducting, and so it will get a high signal from our 100K pull-up resistor. When B is low, we'll get an output high. So it's basically really simple inverter, and I use this very commonly. It's super reliable in these types of circuits. So let's build that up real quick. We have coming from our output B here, from the same place that we are pulling through our 1 meg to give us our indicator. We're going to do the same and send it to the base here of our transistor, and then to our collector we're going to have the 100K pulled high, and then the emitter is going to be pulled directly low. And now, just so that we can see what's going on from the collector here, we're going to pull another 1 mega ohm resistor to the base of our transistor here. And this circuit is identical as these ones here. And so you can see that each time that this one goes low, this will be high. And of course you could have just thrown like a 4069, I believe it is, IC in here that has 6 of these inverters in here, and they could come very well handy in later in whatever circuit you're building. Maybe you have a spare inverter and an IC hanging out, and you can use that just as easily. However, most of the time I'm trying to use as small as a footprint as possible, and I really enjoy using the transistors just because it really simplifies things, even though you do have to use resistors to bias the transistor appropriately. So here's the pinout for the CD4029, which is an up-down presettable counter. It can count in binary or decimal here, and however, the pins that we're going to be interested in right now are going to be the clock pin and the up-down. Here they are again, and basically it's going to be the same as with the digital potentiometer, except instead of just plugging in directly from B pin, we're going to be inverting it first. So here that is right here with the inverted circuitry, and it just goes right into our clock pin. And I have this 300 picofarad capacitor here just because it kind of acts funny unless that's in there. It helps stabilize the clock pulse a little bit. And then into the up-down counter, we just pull directly from our A pin, and all of our jam inputs here, also called the preset pins, are pulled low. It does work fairly well though. Each time that you give it one rotation, it counts a bit, and if you turn it counterclockwise, you can count downwards, which is pretty nice. And however, it still is not perfect. It will every now and then skip some of the steps, especially the faster you go. A nice thing about this this chip too is that we can connect to the preset enable pin instead of just having it pulled low here. We can connect our push button to it. So just by adding a pull down resistor right here, we can count like we were before. However, anywhere within the count, we can clear it by pressing our momentary switch within the encoder, which is a handy little little feature that you can utilize that for. So just to give a quick example of how accurate this is, we will place the rotary encoder pointing this way and just return it to that position, and you'll see that it kept accurate, and it can be fairly accurate. Now you'll see there that it has picked up an extra bit, so it's not 100% when you return it to its original position. It will sometimes get out of phase there. And the reason this happens really is not even a fault of the circuitry and it missing steps. What's happening is that it's only going through half of an indentation. So you'll see that this is going low, B is going high right here for the clock pulse, and so it will increment it will count it as a full step, even though you're not turning it completely. And that is a fault of this circuitry. And eventually, as you turn it, you'll only do half a step that you didn't want to, and your step will get out of count. Now, if that's really important, there's several things that we can do to make that better. But let's look at one way to improve this type of signal processing and decoding, so that half turns don't cause errors further down in the signal processing. To clean up our signals a little bit more and get consistent information, we need to look at our dissection here of our signals. And if, as we saw earlier, we turn the knob through half a rotation, our clock signal that we're referencing here from B may be giving data and referencing A at times that we don't want, and depending on the application, give us results that we really don't want. So in order to solve that, we can reference both signals together. and create a clock pulse separate from both of these, or that's relying on both of these to go through a full turn, or through this entire process right here, from going from both on to both back on again. And to do the same with our up-down count, to make that a little bit more reliable, rather it just being a pulse that's being referenced here at A, the best way I've found is to create a lock that goes high or low and stays high or low, no matter if you're turning it or not. And usually, when you turn the rotary encoder, you're doing it more than once in one direction or the other. So it's good to keep that up down permanently high, as long as you're continually turning it to the counterclockwise or clockwise. And so in order to create our up-down signal, we also want to reference both A and B and lock the signal in place. There's a lot of ways to do this. The one that I devised, though, with the fewest components and the highest reliability, takes a look here, and every time that both A and B are low, this is the period in which we want our clock pulse to occur. So right during these periods. And that avoids a lot of the clock information that we saw earlier with the 4029. And so only when both of these signals are low will we create a clock pulse. And as I said earlier, most ICs that you interface this with are going to be looking for this rising edge. So that's what we're going to devise here, is something that gives us a positive going pulse every time we want the clock to be activated. Now for our up-down counter, it's important that every time we have a clock pulse, that the counter will go high before we get our clock pulse, our next clock pulse that comes in. That way, when we do get this pulse, our up-down signal has been locked into the position that we want it to before our clock comes in. That way, when we turn it, let's say clockwise, it doesn't decrease the count or give us a signal saying you've turned it counterclockwise when you have in fact turned it clockwise. So it's very important that that we use the information from the first part of our dissection when one of the clock pulses goes low before the other. So here's the simplest way that I've found to process both A and B at the same time to give a little bit more reliable clock pulse and up-down signal information. So if you reference both A and B through a NOR gate, that gives you a clock pulse, as you can see with the truth table here, every time that A and B are both 0, which through these signals you can see that's what we're looking for, is right here in our clock pulse time, we want both A and B to be 0. So once we put it through our NOR gate, we very simply just get our clock pulse that we're looking for. Now to get our up-down counts, it's a little bit more complicated, but still fairly easy. Just sending both A and B again through a not AND gate or a NAND gate will give us this truth table information, which is that our output will only be 0 if both A and B are 1. which essentially means that it's going to be giving us a 1 any time that we're not turning the rotary encoder. But as soon as one edge falls, either A or B, it will give us a 1, which is what we're looking for. Is basically it's a falling edge detector, whether it be A or B. And so that information we're going to send into the clock pin of a D-type flip-flop. And we call it a D-type flip-flop because it takes data in, and every time that there is a clock pulse, it will reference the data and determine whether or not the output will be high or low. And so if we just use our A pin as a reference, as we did earlier, any time that A or B goes low, it will reference A and then lock into position our up and down. So of course you could implement this with various integrated circuits that have a NOR gate and a Nand gate and D-type flip-flops. However, I managed to find a way to do it using just one dual-type flip-flop, a 4013 IC, 2 Npn transistors, and a couple of signal diodes, such as the 4148, I believe there are, as well as a couple of the pull-up resistors and biasing resistors that you would need for these. So let's go ahead and take it to the breadboard and see how we do it. The first step to this circuit is going to be to invert both the A and B signals with Npn transistors. Very easy to do. Both of the bases are going to be biased by the 100K that is already built into our debounce circuit, the breakout board. And so you just connect the output directly to the base, and then your emitter to ground for both of them, and then your collector through a 1 mega ohm up to 5 volts. And so your output you take from the emitter, the collector after your mega ohm. And the result of that is going to be just an exact inversion of both of the signals, so that you get positive going pulses versus negative. And so after that is going to be an imitation of a NOR gate, which is what it's going to do is to take both of the signals to reference both A and B, the inverted versions, and every time that one of those goes high, it will go through these signal diodes and activate the clock on the positive going pulse. And so depending on whether or not A, which this is being referenced right here to A, is high or low, the data of this D-type flip-flop will set our negative, I'm sorry, not negative, but our inverted Q output to our up or down count. So let's go ahead and build that up real quick. So here's our dual type flip-flop. This is the CD4013. I'm not sure if you can see that quite. There it is. And these are a fairly easy pinout. It's exactly identical on both sides. And so you can see that when we rotate this clockwise, we get a positive here, and when we rotate it counterclockwise, we get a negative. So let's go ahead and talk about the second part of the circuit, which uses both the A and inverted A and B signals here. However, we have these 4148 diodes, signal diodes. However, they're facing backwards and both of them are connected to the set pin of our D flip-flop, wherein the set and reset pin before had been pulled low. The reset is pulled high, and the set is pulled low in this case, but only pulled low through these diodes when both of these have been pulled low. And what that is imitating is the Nand Gate here, and you can see that what's happening is that only when both of these are ones, or since we actually have inverted our signals here, only when both of these are 0 will it give us a 0. And once a 0 is present here at our set, what that will do is it'll set our flip-flop on, and then it will get reset as soon as this is no longer being pulled low. It will reset and go back to a low again. Maybe that's a little confusing, so let's go ahead and build it up so you can see it working. So you can see now that only when both A and B are high in the inverted will our clock pulse go high. And as soon as it's no longer both high, it'll go off. And so it gives us a very sharp, short clock signal that's still very reliable. And it's very important the way that it interacts with the up-down, and that if we change position, we change direction that we rotate it. So I'm going to rotate it now clockwise. This will illuminate before our clock pulse will occur. And same if we rotate it counterclockwise, the up-down will indicate, okay, we're going clockwise or counterclockwise. Give it a clock pulse. And that way you'll never get an accidental clockwise versus anti-clockwise signaling. And it's good practice to pull your clocks and your data. You can see that I just left them floating here. So let's go ahead and pull these low, just to make certain that no stray voltages cause random clock pulses. My frame rate here on my camera is not good enough to catch it when I'm moving very fast, but this is extremely accurate and doesn't really cause any sort of malfunctions, and it's much harder to get a incorrect read by half of a turn, because these are much crisper of a signal. And so as far as a real application of this, or at least how I've used it, this is a 16-step sequencer that I made for a synthesizer, and I never, or I haven't yet, incorporated it or built the synthesizer that this goes into yet. But I use this mainly as a way to just learn more about how to build complex circuits based around just a rotary encoder, and to be able to do things that with just as few amount of controls as possible, that's still interesting and user friendly. So you can see here that there's a decent amount of logic chips and all sorts of things in this stack here, and that's all written out right here. But essentially, what this does, here, let me just get it started here for you. What this basically does is allow you to control the sequence order that it's played in, and so you can send different bits of information into the clock. Each time you press the button, it selects one of the parameters. This basically represents the binary of what's going on here, and of course 4 bits of binary you can count to 16. So if we turn it up, it will start counting. I can control up to, I believe it's 4 different bits, and so you can see here that it's counting. Let's turn up the speed a little bit. So we can get that bit set, and it will continue to count on that clock. And you see that you can get some complex counts that you wouldn't be able to get with your normal 16-step sequencer because you have control over the bits that are counting. I don't know how useful it's going to be in a musical settings, but I liked it a lot as a means of just learning how these things work and how you can use them. This too is a swing, and it just offsets one of the counts a little bit. Each of these is just a voltage divider that you can send out as an output to an oscillator. That's the plan with it. As of right now, it's just a pretty light show. And this is just another version of the same thing we just made, which is basically this circuit here. But I did it in with Npn transistors. I actually used 5 BC547s and in a different configuration than these, and technically almost all of these actually are inappropriately hooked up, you know, not the way that you're supposed to, but it works pretty darn well. I've been using it for a couple different applications. The one that I made it for specifically, or I designed this circuit for, was for one where I had a very tiny little bit of room to slip this in, and there was already not enough room in the enclosure as it was, and so I needed something that just fit in there, and so this was a pretty good solution to it. And I also built in some LED drivers here. These are surface mount NPN transistors right there. Oh, come on. These are surface mount NPN transistors and some surface mount LEDs. But it has the same sort of reliability. So maybe I'll go over this in another episode. This one's already turning out pretty long, and I'm tired. It's time for me to go to bed. So thank you so much for watching, guys. If you have any questions, as always, feel free to contact me in the comments, and I'll do my best to answer and post more videos on it. So have a great evening.